And we're back, and today we're going to talk about operational amplifiers. So, last time when we left off, we were trying to discuss devices that would increase signal rather than decrease signal. Instead of attenuate a signal, that would make the signal better. In other words, we're after switches or amplifiers. And we dealt with a couple of types of these. We dealt with the relay, which is a kind of switch, and we dealt with the transistor, which can act as an amplifier or as a switch. But transistors by themselves are actually very difficult to work with. They have very sophisticated response curves that are not linear. They've got all sorts of conditions. They only work in one direction because of the charge carrier sign. So in order to create a proper amplifier circuit, you need at least two and sometimes many transistors. Now, rather than design our own transistor circuits, it turns out that very frequently you can bundle all of these into a single package that is a very versatile instrument. And that's what we're going to talk about today, is those instruments, which you can easily buy and do all the job that you need to create useful circuits. So the name of these devices is called an operational amplifier. Now, an op-amp, as it's called, is a device that's made up of transistor circuits. Now, these are not trivial devices, as I can show you here. This is the 741 op-amp. This is a very common device. We'll be using 741s or 411s, which is its predecessor, throughout this lab. And you can see there are many transistors and resistors and capacitors and inputs and outputs. Now, back in the times when you would have a transistor radio or a tube radio, where these would be tubes instead of transistors, this would be what the circuit would look like, and this would be each of these guys would be those little transistors in your kit. Now, since the 90s, this is now available, or the 80s probably, this has been available in the form of a chip. So you have a single chip which then can do all of these functions. So the chip is usually inside a case. The chip itself is never visible. The chip is always inside a case, and it's got pins coming out, and you can connect things to those pins, and everything goes on. And inside, the actual chip is usually quite small compared to the casing. Especially the casings we're using. We're going to be using casings that are called DIP, for dual inline package, and that is the spacing that you use on a breadboard. And we'll come back more to that later. Anyway, to an operational amplifier. So what it does is it can amplify things. And we're going to use a symbol to describe that massive circuit instead of redrawing it every time. So we're just going to use the symbol is just going to be this. It's going to be a triangle with two inputs, which I'm going to label as minus and plus, and a single output. I'm also going to draw on here two lines that we'll actually need in order to make the operational amplifier work, and that is the power supply. So, and that's usually we drive an op-amp with plus and minus 12 volts or plus and minus 15 volts. So I'll put those on here. And we can connect various things to the circuit. Now, the basic operation of what an op-amp is the circuit compares the voltage on the V minus and V plus input lines. And it works this way, so it basically subtracts the voltages between these two. And so it computes in an analog fashion by subtracting two voltages. It finds V plus minus V minus, and then it multiplies that by its gain factor. And this gain for a typical op-amp chip is something like 100,000, which is a lot. And it's going to set the V out equal to that. Now, this is not quite the whole story, of course, but this is what it does. Now, why would we want this massive, massive gain? Well, the reason is because we never just use the op-amp bare like this. In the first part of Lab 5, you're going to hook him up like this and just put some voltages on here to see what the output looks like. But in reality, this is a very this circuit is not really designed to be used this way. In fact, what you'll notice is that if these two guys are different by even like a millivolt, then this guy is going to be like 100 volts. Well, of course, the output can't be 100 volts or minus 100 volts because its power supply is coming from this plus and minus 12 volt supply, which is coming from a power supply or a battery that's outside this unit. So that means the V out can only be within that range. Let me see, I've got this the wrong way around, don't I? No, yeah. Okay, minus 12 volts is less than plus 12 volts. So this must be the condition for the output voltage. It can't give out an output voltage at any time that's larger than the two input voltages. Actually, this isn't true of tube circuits. Tube circuits actually can slightly overdrive for very brief periods of time. It's one of the reasons audiophiles like them. But that's a side point. We don't really care. So the output can be anywhere between these two. That means that if I have, like, on V minus, if I have, like, 0 volts, and on V plus, I have 0.1 volts, then V out, according to the equation above, should be something like, 1,000 volts. But that actually can't happen because it'll just drive up to the 12 volts. And that's called hitting the rail. It's called, so these two voltages frequently on the breadboard. So when we attach these circuits onto our breadboard, so here's a breadboard row, here's the trough in between two breadboards, here's a breadboard row, and then along the side of the breadboard you've got these vertical lines, and we call these things rails. Like they're like railroad tracks. And frequently we'll use these guys to power the plus and minus 12 volts. So we'll carry ground and plus and minus 12 volts up and down these dual rails that go up and down your breadboard. And so frequently, so for instance, your chip will be sitting right here, and here your 12 volt connection will be connected to one of these, and your minus 12 to the other one. And so when you have the voltage supply, the output voltage hit these values, we call that hitting the rail. So it hits the maximum or the minimum output voltage that it can. And this is quite a common thing, and you'll be seeing this happen all the time. So if ever you're asking this thing, you ever put inputs in here that exceed some value, it's going to hit the thing. So in fact, in order to have the output value to be somewhere between minus 12 and plus 12 volts, these two have to be almost exactly the same in voltage. So that doesn't sound very useful, but it is. A couple of other things to note about operational amplifiers is that the inputs have very high impedance. That is to say, if I connect something to one of these inputs, to like the V minus input, so let's say I have some circuit over here that's going in. What this circuit sees is it sees a resistance to ground with an R that's much, much bigger than a mega ohm. That is to say, that these things never accept very much current. That never do you have to put in much current into these devices to make them work. Obviously, a little bit of current has to trickle from this to ground, or trickle between these two, or trickle somewhere. This thing can't have zero current coming in, but it is a very small current, and that is actually one of the primary design considerations in choosing an op-amp, is they have very small, very, very large input impedance. Similarly, they have very small output impedance. That is to say, if you draw the output section of this thing, and you're going to do a Thenovin equivalent circuit for whatever comes out here, then this Thenovin equivalent circuit will look like a power supply that's changing over time and have a very tiny R. And so if you have a changing voltage here, that's whatever's going over here is changing the output voltage. That acts like a voltage source with a very, very tiny output resistance, like a battery or like a voltage supply. In other words, this thing can drive massive currents no matter what voltage is being asked to do. So this thing acts like a time-responsive battery or a time-responsive voltage supply. Okay, so we're never ever just going to run an operational amplifier like this. What we need to do is we need to adjust it so that the inputs are close to each other, and use that to drive the output in a meaningful way. And to do that, we need something called feedback. And feedback is the crucial part of any circuit. In fact, what we want here is negative feedback. We don't want the thing running away off to the rail and hitting the rail. We want to rein it back in and just give the amount of voltage that we want. So we're always going to have a circuit where we have some kind of connection from the output back to the input. And that allows you to regulate the outputs. The output is always right close to the input. And so when we design a circuit like this, it's very analyzing, this monstrosity is impossible. So instead we're going to use an idealization of what an op-amp does. And to do that, all we need are two magic rules. If you have a well-built op-amp circuit, the op-amp will obey these two rules. And so these are the two rules. Rule 1, the I into the V minus and V plus inputs is 0. That is to say, it's an infinite input impedance. No current flows in or out of these terminals. No matter what you're doing on the left-hand side, no current will go in here. So it acts like a voltmeter, or it acts like an oscilloscope probe. These guys are only sensors. They don't actually do anything. That's the rule 1. That rule is pretty easy. Rule 2 is V out will be such that V minus equals V plus. What does that mean? The op-amp will do whatever it needs to in order to make these two values the same. The voltage on the negative input and the positive input, and I should label those the negative and the positive. That the voltage on this pin and the voltage on this pin be the same. And it will change the output voltage until that is true, and it will do that very quickly so that the output will always track to keep this rule correct. You think about it, if I'm connecting the output back up to the negative input, if the output's too high, it raises this voltage, which lowers the output. And that's basically what we're talking about with feedback. All right, so let's walk through an example here. There's two important examples I'm going to do today, and these really are the core of op-amp circuits. And once you understand these, you can understand the rest of them. This tells the story. And you should be able to walk along with me, at least on the second one, once I get there. So I'm going to show you the circuit that we're going to use for the very first thing. And this is like the most important op-amp circuit. It's called the inverting amplifier. Inverting amp. So in an inverting amp, I have my op-amp, and I'm not going to bother showing the power connections anymore. Those are always there. You have to have the power connections to plus and minus 12 volts. But I'm not going to bother drawing them on because they're not really an active part of the circuit. They're just a necessary condition for making it work. So then what I'm going to do is I'm going to have an input from somewhere, and I want to make that input bigger. Or I have an input from somewhere, and it's got very, very small current that it can supply, and I want to drive it so it's got a bigger current. So in any case, I've got a small signal I want to turn into a big signal. So I have some sort of input signal here that I want to make bigger. So the circuit I'm going to use will look like this. I'm going to send that input signal in relative to ground. I'm going to send that in here. And so I'll call this, I'll just call this Vn. And I'm going to send it through a resistor. And that's going into the negative input. And the positive input I will tie to ground. And then I'm going to make a connection right here, bring this up, and put a feedback resistor here. I'm going to label this thing RF, and I'll label this thing R in. This feedback resistor, I'm then going to connect to the output, and then this will be the out. So that's going to be my circuit for the inverting amp. I can feed some time-varying signal into here, and I'm going to look and see what time-varying signal I get on my output. Now, in order to analyze this, we're going to use our two magic rules. So the two magic rules are that no current goes in or out on these 2 points, which is to say that if I have any current going this way, which I'll label with an I I have the same current going through this resistor. So any resistor going through here, none of it can get into the chip, so it all must go this way. Okay, so this is what it looks like. So that uses rule 1. Rule 2 is that V minus is going to be equal to V plus during the operation of this amplifier. So that is to say, the voltage, it will change this output pin so that the voltage here and the voltage here are the same. Now what that means is that basically this point right here is like it's connected to ground. That is to say, I know that this pin, during normal operation, this pin will be at 0 volts. Now no current flows into that ground, but I know this is going to be at 0 volts. All right, well now I can start analyzing the circuit. If this thing's at 0 volts and this is at V in, then I know this relationship here. I know V in minus 0 volts, the grounding voltage here, is going to be equal to the current going through that resistor times the magnitude of that resistor. Oh, my camera's all cattywampus this way. How did that happen? So I know that this is the difference in voltages from here to here. I'm going to draw the current going to the right, so this is at higher voltage than this. And I'll say Vn is positive for now, just to make it interesting. And I will be then to the right, and and I times R is going to be the difference in voltage. But I also know that if this is at 0 volts and that this is at some other positive voltage, I know that V out minus 0 volts, so this minus this, is going to be equal to I times RF. But I have to put a minus sign in front of this. Why? Because if the current is this way, then that would mean this is at higher voltage than this, and so I have to take this voltage minus that voltage. So in other words, 0 minus V out, or that's the other way I could write this, is 0 volts minus V out is equal to I times RF. Okay. And this is true at any moment for some value of I, which is also changing over time. As we change the input voltage, the current changes, and as the current changes, the output voltage changes. Okay, so now I've got these two equations. Now I just have to put them together. I can solve for I. So I here is equal to V in over R in. And over here, I can find that I is equal to negative V out over RF. So now I just need to stick these two together. So this means V in over R in is equal to negative V out over RF. And then the solution to this becomes quite straightforward. What we get is V out is equal to negative V in. So V out is equal to negative V in times feedback resistor over the input resistor. So that is the net thing for an inverting amp. Now we can change these values to be whatever I want. So for instance, if I put RF is equal to 10K and Rn is equal to 1K, then V out is going to be equal to negative 10 times V in. That is to say, if I have an input voltage that looks like this is like between 1 volt and negative 1 volt, then the output will be the same as the input, except it'll be between 10 volts and negative 10 volts. But except this isn't right because I need that minus sign in there. So in fact, what the output will look like this, right? It'll be the invert. I didn't draw that very well, but I'll have the inverse of the incoming wave. So when the input, so to draw these on the same scale, if the input looks like this, the output will look like that. It'll be 10, and this will be 10 times bigger than this. Now, this works perfectly well. Now, an inverting amp, so could you consider that what the signal you're feeding in maybe is the output of a microphone. or your iPod or phone or whatever, and you want to amplify that signal so you can play it through some big speakers. Well, this does your job. It takes a small signal and turns it into a big signal. And furthermore, the output of this thing has got, because it's connected directly to the op-amp, there's no output impedance to speak of. So this thing can drive very, very large currents. More to the point, you get an amplitude change here, but now it's inverting, but who cares, right? If I've got a sound wave, our ear cannot detect the difference between a sound wave that starts as compression and ends in rarefication, or starts in rarefication and ends in compression, right? We just can't tell the difference. We have frequency detectors. We don't really have phase detectors. So our frequency detecting ears can not tell the difference between these two waves. We hear that there's an initial shock, but we don't, that's like a drum hit or whatever. We can't tell which of these it is. So as long as we're inverting everything stays the same. Now, I might get confused if I have an inverting and non-inverting signal and they mix together, then I might get a beat pattern, I might get cancellation or something like that. But this is really quite straightforward, right? We can do this no problem. In fact, that's how you make noise canceling earphones, is you just have to put them through an inverting amplifier and tie with a little bit of phase delay, and so that the incoming sound and the outgoing sound are out of phase with each other and cancel. So that's an incoming amplifier. Now, there's a couple other features of this thing, an inverting amplifier. This is another couple of features we should probably discuss about this before we move on. So one feature in particular is if we look at this guy, again, one thing we can see that is if I put a V in here, it has to supply this current I. So whatever this voltage source is, it has to provide current I. And so how much current does it have to supply? Well, we know that this current is going to be equal to Vn over Rn. In other words, what this guy sees is basically, because there's this virtual ground here, right? There isn't really a ground, but it acts like a ground. This thing, the voltage at this place is 0 volts because this one's at 0 volts. So this thing manages to change this output so that this is always at 0 volts. So it looks from the perspective of whatever is injecting this signal, it looks like it's driving something that looks like this. So it looks like this is the size of the input resistance that it needs to drive. Now, there's no reason, though, that we can't make this input resistance quite large. Now, when you make it too large, the op-amp actually can't operate. But if you can make it quite large, so if I want to get that 10-to-1 ratio, there's no reason why I can't have it be like 100K to 1000K to 1 mega ohm, right? And then get my 10-to-1 ratio that way. So I could have this Rn could be a very large resistance, which means this thing only has to provide a very, very tiny, like a fraction of a milliamp of current. So that's nice. It's not perfect. We would like it to be we might like the input impedance to be infinite or very, very large, but we can still tune it the way we want. So that's what the input impedance of this guy looks like. The output impedance is similar. This output thing needs to drive this guy, but this guy can drive almost anything. So this thing has a very, very small output impedance. Excuse me. All right. So that's the inverting amplifier. Another thing, of course, to note is that the output voltage is equal to negative Vn. Right? Is that if the output voltage ever exceeds the supply voltage, either exceeds like more than 12 volts or less than negative 12 volts, it'll hit the rail. So, for instance, if I feed in with that 10-to-1, if I feed in like a 2-volt signal, then the output will stop and hit the rail because it can only supply 12 volts in the output, right? If I have a 10-to-1 amplification ratio, if RF over Rn is 10, then that means it will be trying to make a plus and minus 20 volt output. And of course it can't. So what it will do is you'll see something that looks, it'll go down first. It'll go down and hit the rail and come back up and hit the rail and come back down and hit the rail, where this is minus 12 volts and this is plus 12 volts. So it'll hit the rail, and then go up, and then hit the rail, and you have a problem there. Another limitation, that's an inbuilt limitation from the op-amp, is that the op-amp can't respond instantly to changes. That whole circuit takes a small amount of time to change. And there's a couple of different ways that we can describe that operational limit. And that operational limit is, so one of them, which is kind of the easiest thing to do, is called the slew rate. And that's dV out dt. That is to say, there's a maximum rate at which it can change the output relative to the input, right? Your input might be changing very rapidly, but the output can't change instantly. There's a limit to how steep this line can be. And that line can be very, very steep. So this rate is in, many, many volts per second. But so it could be that it lags behind. Now, one of the implications of that is that if my input is a very, very, very fast oscillation, the output can't quite keep up with it. And so all of those high rate things will get suppressed because it can never quite keep up. So if I have an input that looks like this, my output will look right, but it'll actually be greatly suppressed because the thing just can't get far enough in that time. And so that leads to, so another way you can describe the slew rate is as a maximum frequency, or a maximum frequency at which this thing starts to not work so well. Now, in fact, it isn't a maximum, because it just turns out that if you give it higher and higher frequencies, it'll still do its job, just worse and worse. So what that means is, in fact, there's just a place where the op-amp starts to work less effectively, and the place we could code is called the 3 dB point, and that is basically the place where the op-amp is only half as effective as it needs to be. And so we have a frequency at 3 dB, which describes the maximum frequency at which this op-amp can operate and still do a job close to what it's supposed to be doing. This is the place where it's half as effective as what it should be doing, where the power output is half of what it should be. Okay, back to some circuits. Let's do one more circuit. So let's do a second circuit here, and this is going to be, we did the inverting amplifier, so we're going to do the non-inverting amplifier. Okay, now this one's a little bit trickier to draw, a little bit trickier to understand. So I'm going to draw it. I'm going to be careful here. I'm going to draw the op-amp differently. There's nothing saying we have to put the -1 on top, and so I'm not going to. So this one has the V-in connected directly to the positive input. Now we still have to have some feedback though, and I'm just going to draw the circuit. I find it easiest to draw the circuit like this. So I'm going to call this R2, and I'll connect from there to the minus. And I'll call this R1. So there's my circuit. Okay. So this thing's still got feedback. I've still got, whenever the output is too big, it creates a voltage here at the minus side, which is not what we want, which is bigger, and so that'll always work to suppress massive fluctuation when the output gets too big. We still have negative feedback. Let's see what we can do with this. So we know, and actually at this point you should pause this video and attempt to solve this circuit using the two magic op-amp rules that we had before, that In equals 0 and that V minus is equal to V plus. So right now you should pause the video and attempt to figure out what the output voltage is as a function of the input voltage. Okay, I assume that now you have gone and done this. Let's see if you had the right answer. So let's assume that we have a current going this way, I'll call I. Now, we know at this branch point, no current can go this way because no current can go into the chip here. That's rule 1. So that means that all the current that goes through this one must also go through this one. Okay. Well, now I actually have a metric for this. If I know that I have V out here, and there's a current running through here, I know that V out is going to be equal to I times R1 plus R2. That's the total resistance of this leg here. So the full total voltage drop from here to here has to be V out, and that's I times R1 plus I times R2. So the voltage drop here and the voltage drop here, which gives you that. Then we also know that the voltage here must be, so I'll call this V minus, that V minus must be equal to I times R1, right? So if the current is going that way, that means that this is at a higher voltage than here, so this voltage here will be I times R1. But we know from rule 2 that this thing will always set the output voltage, so the output, the voltage right here, which is the same as the voltage right here, will be the same as the voltage on the plus side. So that means that this is also equal to V plus, which is also equal to V in. So V in is equal to I times R1. V out is equal to I R1 plus R2. Again, solve for I. So, for instance, I can solve for I over here. So I is equal to V in over R1. So I stick that in there, and I get V out is equal to V in over R1 times R1 plus R2. Oops, my pictures. My ugly mug is blocking the picture. So just to write that again, so for this circuit, I've got V out is equal to V in R1 plus R2 over R1. Let's simplify that just a little bit more. That's the output of the inverting amplifier, of the non-inverting amplifier, I should say. Now, this has got the nice property that there's no negative sign anymore. The input and the output are the same, except they're different by this factor. Now, one of the limitations of this, though, is you'll notice there's no value of R2 and R1 that makes this coefficient less than 1. That's impossible to have, because these are always positive numbers. So this is always going to be a rational number. It could be a small rational number, but this will always be greater than 1. So that means V out is always going to be bigger than V in. That wasn't true before. Before, we could have set up the inverting amplifier so that the output was smaller than the input. Why would you want to do that? Well, again, maybe you want to make the output smaller, but you don't want to put a big resistor in there because your driving circuit just can't provide much current. So there's that. So for instance, if you wanted to build a volume knob, you'd probably want to use the inverting amplifier because you want the volume to go all the way down to 0. In this case, you can't do that. So that has got a major limitation. But the output is now in phase with the input. So when the input is doing this, the output, this is time, this is voltage, the output will be doing that. It'll be bigger by this factor, by that factor. And incidentally, this will be, that's the gain, because V out over V in is the gain, which will be 1 plus R2 over R1. So that's the gain of the circuit. It increases the output by that much. Before we were doing the filters, the gains were always less than 1 because it always reduced the amplitude of the output voltage. Here, we can increase the output voltage. Now this phase change, like flipping it upside down, doesn't matter very much. And so for an audio circuit or any other signal processing, remember, we can always chain together 2 inverting amplifiers, and so that's not really a big limitation. And this is a limitation. This does limit how the circuit works. So in fact, it's maybe not be obvious, but this is actually the guy that has less utility. But the non-inverting amplifier has got one really important advantage, and that's this: that if you look at it again, no current gets pushed into the op amp from the input source. That is to say, this thing works like a perfect voltmeter, that no current goes in here for an ideal op amp. Real world op amps, there is actually a very small current, as we discussed. There's a very large input impedance into the op amp, but it's really, really big, which means this current is really, really small, which means you can touch this thing to a very sensitive input. So you can have an input that can't drive much current. So for instance, a photodiode or some other really sensitive sensor that only can put out a tiny, tiny bit of current. That's how you can do this. And in fact, voltmeters will use this arrangement in order to make a voltmeter. This is what makes a voltmeter. A voltmeter is, or an oscilloscope. An oscilloscope is the very first circuit that you encounter looks something like this. It isolates the input from the output. So even if you made this gain, even this gain isn't very big, that doesn't matter. What we've done is we made it so that I can make, and this thing of course can be attached to a tiny little resistor, right? So like a 10 ohm resistor, like a speaker or something. And it can drive that no problem, even if this guy can't drive anything. So the advantage here is a very big input impedance. And that's the real advantage to an inverting amp, to a non-inverting amp, I should say. Okay, almost done. So these operational amplifiers, like these triangles, they are very, very nice devices that are very, very flexible. I'm going to go over a couple other circuits in the next lecture, but before we move on, I just want to, sorry, I had to go get my piece of paper. I wanted to go over a data sheet. So a data sheet is a document that comes with any, well, it doesn't come with, but you can print out for any device that you buy. And the data sheet tells you the specs for that particular unit. Now, up till now, we've been using capacitors and resistors, and their specs are really not very interesting. A resistor spec is within 5%. You can color code that on the actual resistor. For more complicated devices like chips, at this point, we need more information about how to use it. And the data sheet is your friend. And so a data sheet, they have different fonts and slightly different layout, but they always look something like this. At the top is always the name. So this is a particular model of an operational amplifier called an LF411. The letters frequently refer to either technologies used or specifications. The number part of it, which sometimes might be broken up with letters, that's the part that tells you what thing it is. It's a JFET, junction field effect transistor. Hey, we learned about field effect transistors last time. A JFET input operational amplifier. And here are some of the things, this is kind of the advertising layer. These are the reasons you might want to use this unit. There might all be reasons you not want to use this unit. You might want to use a different operational amplifier, but this is telling you some of the things you want to know. So for instance, this thing doesn't use very much power. It only uses 2 milliamps typically of supply current. It's low input bias current, low input noise current, low total harmonic distortion. That is to say, it doesn't affect your frequencies very much. And this thing talks about the package. Now, this is a picture of the unit, at least in schematic, and this is for the DIP dual inline, DIP dual inline packaging, which is the kind that you're going to use in your thing. So what you do is you take the chip, and it looks like this. And every chip has something like this. There's a notch at the top of the chip, or sometimes there's a small circle in the top left of the chip. So looking down with the pins facing away from you on the chip, this then tells you the layout. Pin 1 is always on the top left corner of a chip, and the pins are always numbered down the left-hand side and up the right-hand side. So pin 1, pin 2, pin 3, pin 4, pin 5, pin 6, pin 7, pin 8. You'll notice that on this one it says there's an NC, which means that this pin isn't actually connected to anything. You'll notice that there's an in minus and in plus, that's the V minus and V plus lines that we labeled, and there's an out, and that's the V out line we labeled, and then there's these two, VCC minus and VCC plus, and those are, VCC usually responds to supply current, supply voltage. So these are reference voltages or supply voltages, so this is the power connection, so this is where you place plus 12 volts, and this is where you place minus 12 volts, or whatever you're using for your supply. So this is V minus, V plus, V out. These balance ones are generally not used. There are ways of tuning the circuit precisely. I have never actually used these in a circuit, so you can basically ignore them, leave them unconnected. Right? And so here it is in schematic. Pin 2 is the negative input. Pin 3 is the positive input, and then pin 6 is the output. So this is just describing it to you again. Now, a data sheet has got tons and tons of information, right? So here it tells you can plug, this thing can take up to 18 to minus 18 volts. This is the absolute ratings. It has differential input voltage, plus or minus 15. Duration is short output circuit, right? So there's a bunch of things. For instance, there's the properties of it under different temperature conditions. They're here. Now, in tables like this, you'll notice there's a whole bunch of things. So these are parameters of how this thing behaves or what it needs in order to behave. And over here is the typical value. So for instance, input offset voltage. Now I don't know what this is. I'd have to go look it up, read the rest of the data sheet. Let's find one that's more interesting. Let's say input resistance right here. So we know what that one is, the input resistance. And so this is under normal room conditions at 25 degrees C. It says that the typical input resistance is 10 to the 12 ohms. Wow, that's a lot. That's much more than mega ohms. That's giga ohms, right? So it's not even giga ohms. That's tera ohms. Okay, so that's massive. That's a huge, huge input resistance. This is a really good operational amplifier, right? And then it also has the negative and maximum ranges. Now what this is for a typical unit. When you get a chip, it will have these values, but it could be anywhere between these two values. And what they're saying is they're guaranteeing that your chip will operate somewhere in between these two values if they list them. They're saying, unless it's like a really dud chip or there's a manufacturing flaw, that each device will be between these. Some very high expense components will have very narrow ranges for this. And in fact, if you ever find a military spec part, it will tend to have very narrow ranges and be hugely expensive. Never use military spec parts. They're totally pointless. Let me see, what else we got here? Some operating characteristics, and then we've got some notices, and then we've got packaging information, how many come in the package, system on chip. This is the box they come in. This is the chip. So this is a variation of the chip that does solder connections that you'd find like on a computer motherboard, and exactly how big each of these little bits and pieces are and how much they're spaced out. This is the same thing for the dip chip we're going to use. Exactly how thick are the pins and where are they and what do they look like. Exactly how wide is the thing. Stuff like this. Some of them list even how they're put on the reel, and because you're going to build them. Because if you're a commercial consumer, you're going to build a machine that uses this spec to construct your device. You're going to have an automatic machine which takes this and slots it in. It's called stuffing. It stuffs the chip into the circuit board and solders it in place. You have to know all of those specs going in. Now, of course, we as sort of hobbyist level, we don't care about most of that. So most of what you need in a data sheet is the first 2 pages. One thing, though, to look out for is that a lot of data sheets, not this one, but a lot of data sheets will actually have what's called application notes. And what that is it's basically a little textbook on ways in which you can use this device. The data sheets serve partly as advertising to engineers, but they frequently have very good ideas. And like 90% of the time when you get a device, you're going to use it in exactly the way it lists in one of the application notes. So these data sheets are enormously rich and interesting documents full of useless, totally useless information like 90% of the time. But every once in a while you need to know one tiny little piece of information in there, and it's got it. So from now on, not right now, but in Lab 5, I've given you that pinout, and I've given you the necessary information for plugging this in. As we go on, I'm going to give you less and less information and make you go look it up in the data sheets. All the data sheets are online in the course webpage. Under resources, there's a directory called data sheets, and there that's got PDFs of all the components that we're going to be using in the course. So we're going to more and more rely upon using those instead of really relying on my cheat notes. Okay, I've already gone on for way too long. Next time, I'm going to go over a couple of the op-amp circuits that we haven't already discussed, namely a voltage follower and a summing amp. And so you can wait until you're halfway through Lab 5 or so before you look at that video. Everybody have a great day, and I will see you soon.